PowerPoint is going to cover the modulus function. We're going to have a look at the modulus graphs. Before that, have a go at these quick starter questions. Sketch the graphs of y equals 2x plus 3 and y equals x squared minus 7. Press pause now, and on the next slide I'll show you the answers. The first graph is a linear graph. It has a y-intercept of 3 and a gradient of 2. So this would be my sketch of y equals 2x plus 3. The second graph is quadratic, so it's a U shape. The minus 7 means that it intersects the y-axis at minus 7. So its minimum point is at 0, minus 7. Things that you need to know about the modulus function are what it means, what the graphs look like, and you need to be able to solve both equations and inequalities that include the modulus function. So first of all, what do we actually mean by the modulus function? A modulus function is a function which gives the absolute value of a number or variable. The outcome of this function is always positive, no matter what input has been given to the function. Modulus functions turn everything into positives. The modulus of 3 is equal to 3. The modulus of minus 3 is also equal to 3. So the modulus function is simply giving us the absolute value of the number, ignoring whether it was a positive or a negative. The results are always positive numbers. You could also think of a modulus as being how far away is something from 0. In this picture you can see that both of the numbers 3 and minus 3 are both 3 away from 0. You can also see the notation that we use, these two vertical lines. The two vertical lines mean the modulus of something. The modulus of minus 8 would be 8. It's the value of the number, ignoring whether it was a plus or a minus. In the picture on the left, you can see an accurate drawing of y equals 2x plus 3. This is a linear graph with a y-intercept of 3 and a gradient of 2. If we wanted to draw the modulus of this graph, as we can see with those two vertical lines, the modulus means that the y-coordinates would always be positive. Any parts of the graph that already had positive y-coordinates would stay in exactly the same place. But any parts of the graph that had negative y-coordinates would have to be reflected up to have positive y-coordinates. So we can see that what was originally a straight line has now become a V shape. Here's another example. On the left-hand side, we can see y equals x squared minus 7. But on the right-hand side, y equals the modulus of x squared minus 7. Any parts of the graph that were above the x-axis have stayed in exactly the same position. Those are the bits that I'm colouring in yellow. But any bits that were below the x-axis that had negative y-coordinates, they've been reflected up. They now have positive y-coordinates. And you can see that it's totally changed the shape of the graph. Now that we know what the modulus function is and what the graphs look like, we're next going to look at how to solve modulus equations. I'm going to show you two different methods. In an exam, it would be up to you which method you used. Sometimes method 1 works out better, sometimes method 2 can be better. It depends on the question. If the modulus of x add 2 equals 7, that means that it was either equal to 7 or minus 7. So the first method I'm showing you is where we split the problem up into two separate pieces. And we say that that x plus 2 was either equal to 7 or minus 7. We then have two very straightforward equations to solve. The first one gives us an answer of 5, and the second one gives us an answer of minus 9. That's very often the quickest way of solving a modulus equation. But there is another way to do it, and method 2 involves us squaring both sides. When you square, we get rid of that problem of whether something was positive or negative, because when you square negative numbers, they automatically become positives. When you square both sides, we'll end up with x plus 2 squared on the left and 49 on the right. We can then expand to get x squared plus 4x plus 4, and we can bring the 49 over to the left hand side. As with all quadratics, we want to get one side equal to 0. So if we simplify, 4 take away 49 is minus 45, and then the quadratic, you can either use the formula or you can factorise it. This one factorises into double brackets, and we can see that we get the answers of minus 9 and 5, just like we did with method 1. Here's another similar example. This one has a number in front of the modulus function. 2 modulus x minus 1 equals 8. You must get the modulus on its own first, so that 2 needs to go straight to the other side. 8 divided by 2 is 4. Once you've got the modulus on its own, you can then go back to those two methods that we saw on the previous slide. Method 1, split it up into two pieces. So x minus 1 was equal to 4, or minus 4, and then we can solve those equations. The first one would give us an answer of 5, the second one would give us an answer of minus 3. Your alternative is to square both sides. X minus 1 squared equals 4 squared. X squared minus 2x plus 1 minus 16 equals 0. X squared minus 2x minus 15 equals 0. This factorises into x minus 5 and x plus 3, giving the same answers that we had in method 1. Here's another example where we have the modulus of x squared minus 1 is equal to 7. Method 1, we split the problem up into two parts. If the modulus of something is equal to 7, that means that it was either 7 or minus 7. After we've split it up into the two separate equations, we can solve them. So the one on the left would say that x squared equals 8. So x would be the square root of 8, but don't forget that when you square root something, you can have a positive or a negative. Root 8 can be simplified into 2 root 2. Let your calculator simplify surds for you. Always give your answer in its simplest form. The other equation would say that x squared equals minus 7 add 1, which is minus 6. That has no real solutions. There aren't any real numbers that when you square them would give an answer of minus 6, so that one can't be solved. Method 2 was to square both sides. If we do that on this question, we would have x squared minus 1 all squared equals 49, and if we expanded that, we would have x to the power of 4 minus 2x squared plus 1 minus 49 equals 0. This then becomes a quartic, which can be quite tricky to solve. So, in my opinion, I would abandon that method. This is a good example of where method 2 might not be the best method to use. Method 1 would be a much easier method for this question. You can solve that quartic, it is possible, but it's much easier to use method 1 in this type of question. So we now know what the modulus function is, we know what the graphs look like, and we've solved equations. The last thing we need to do is to solve modulus inequalities. Take a moment to have a think about these two questions. If the modulus of x was greater than 5, what values could x take? If the modulus of x squared was less than 16, what values could x take? Press pause now and have a think. Often the best way to solve problems like this is to draw a number line. If we put 0 in the middle of the number line, and then we start labelling numbers 1, 2, 3, 4, 5, 6, 7, and we could go into the negatives. And if we were solving the first problem, where is the modulus of x greater than 5? That means if we look at the numbers and we ignore whether they were positive or negative, and we just look at the numbers, where can we see things that look bigger than 5? Well, in this sort of area, anything to the right of 5, we would see numbers that look bigger than 5. But also down this end of the number line, to the left of minus 5. If we ignored the minus signs, those numbers look bigger than 5. So I would say then that x could be greater than 5 or x could be less than minus 5. When we use that idea of splitting the problem into two pieces, this number line is going to be very useful. For the second problem, the modulus of x squared is under 16. Going back to that idea of the number line, when you take a number and square it and then look at its modulus, is it under 16? Well, if we started with 0 squared, yes, that would be under 16. 1 squared, yes, that would be under 16. So would 2 squared and 3 squared. Anything under 4 in this region, when we square those x values and any decimals between, we would get an answer under 16. But if we chose some negative numbers like minus 1, for example, and we square it, that's under 16. Minus 2 squared is 4, that's under 16. Minus 3 squared is 9, that's under 16. So now we can see that anything between minus 4 and positive 4, when you square it, would give an answer under 16. So anything between minus 4 and positive 4, when you square it, you would get an answer that's under 16. We're going to use the idea of drawing a number line in our next examples. The modulus of x plus 3 is greater than 5. So I'm going to use the number line. I'm going to identify, first of all, where do I see numbers that look higher than 5? Well, up in this region, but also down here. Anything to the right of 5 and anything to the left of minus 5. Remember that with a modulus function, you ignore the minus signs. So if I was going to split this up into two separate problems, I would say that x add 3 might have been greater than 5, that's this region, or I would say x add 3 might have been smaller than minus 5, that's this region. Now I've got two very simple inequalities to solve. For the first one, we would take 3 from both sides. The second one, we would also take 3 on both sides, and we get our two answers. X is greater than 2, or x is less than minus 8. In this question, the modulus of 2x minus 4 has to be greater than 8. So I'm looking on the number line to see where do I see numbers that are greater than 8. Well, on this side, to the right of 8, but also down this side, to the left of minus 8. So I'm going to say that 2x minus 4 could have been greater than 8, or 2x minus 4 could have been less than minus 8. And then we solve those two inequalities separately. So first I'm going to add 4 to both sides, and then divide by 2. For this one, if I add 4 to both sides, I get 2x is less than minus 4, and then divide by 2, so x is less than minus 2. In this example, the modulus of something has to be under 9. Where can we see numbers that look under 9? There are lots of numbers that look under 9. I'm going to include these ones as well, because remember that with the modulus you ignore the minus signs. Just look at the number itself. Anything now between negative 9 and positive 9 would be okay. So I'm going to say that 2x minus 5 could be between negative 9 and positive 9. This is one continuous piece of the number line, so I write as one continuous, one inequality. On our previous examples, I coloured in 2 very separate pieces of the number line, so I needed 2 very separate answers. But here it can be written as one inequality. I could add 5 to everything to get 2x in the middle. If I add 5, I get minus 4 and 14. And now I can divide by 2.